My name is Russell Sullivan. I'm presenting for the company Cohero, and this is a NearCloud demo, just so I can explain to you guys what we do. We have a bunch of mini data centers spread all over the world, and each one of our mini data centers has a serverless stack and a local data layer. And we have a peer-to-peer mesh that connects them all to do a lot of data synchronization. So we have basically like a content delivery network, but we run serverless plus data way out at the edge. So it looks something like this, and I just use the states here because the image works better with the states than doing the whole world, but we have a worldwide presence. And what our purpose in all this is we want to take the serverless apps you're doing right now, and we want to push them out to the edge. We want to take a centralized cloud app, and we want to spread it out so that you have instances running 10 of them in the States, a bunch in Asia, South America, everywhere in the world, close to wherever your end users are. Just to accurately define what I'm talking about, this is what I mean by a centralized cloud app. It's got an API gateway, it's got Lambda, it's got DynamoDB, and a bunch of devices are calling into a single cloud region. The same application can be run in a decentralized manner, which means that northern device calls into the northern data center, and the West Coast ones call into wherever. And doing so is actually not completely straightforward. There are challenges. I'll get into the benefits in a second. The challenges are the data synchronization part. If you take a single central entity and break it up, the data synchronization stuff is very hard. So we took a long time to solve this, and it is the type of architecture where if you try to do it yourself, or if you rely on, LWW means last writer wins, which is something that's offered by Cassandra or Amazon Dynamo Global Tables, there are serious flaws in setting up your application like that, which I'll get into. So it's an area where you actually want strong data guarantees. You might not want strong data guarantees when you're in a single data center. Like Dynamo doesn't really have like ACID guarantees. But when you start to distribute things over the globe, strong data guarantees prevent actual data corruption that happens quite often. So I'll get into that. So as a visual for the hard part, that little synchronization thing in there, that green that doesn't show up that well, that's the hard part. And when you do it, you get some real benefits. Everyone that's calling into your platform has predictable low latency, no matter where they are. It's kind of like the same thing you get for CDNs with images and videos, you get for your actual web application when you break it up and split it out and run it at the edge. And when you compare that to a centralized architecture, there's a single point of failure, and everyone that's not close to your US East 1 has worse latency. So you get a poor user experience, essentially. So this is a really, really busy slide. We did some benchmarks. Cohero versus AWS, which means API Gateway, Lambda, plus DynamoDB. And I had some friends and colleagues run them from DC, San Jose, Munich, Germany, and Bangalore, India. I tried to make a fairly honest benchmark, which is a bit of a paradox. But I had everyone do it from home, so it's adding in the last mile. We didn't do this from nearby data centers. We pre-warmed all the containers, and the top line here with the 7.5x speed up is kind of a baseline. Both that the DC tester was 20 miles from both Cohero and AWS's data center, and essentially we just invest in low latency, web processing or serverless processing, so we're that much quicker. The numbers get a lot faster. The speed up gets a lot bigger the further you go away from that single US East 1 AWS data center location. And the reason is basically speed of light. If you do a request and it goes across the country, it takes 100 milliseconds, it can take 150. If you're in Europe or Asia, it takes twice, 2 to 4 times that. So what we do is, we invest in latency, and also we spread your business logic and data all over the world so that no matter where your end users are, they get a consistent low latency, how do I phrase that correct? Quick responses. So the main benefits are 10x lower latency, our robustness is better, and then it's half the cost of running on AWS, which when I say that, nobody believes it, so I'll explain later how we do that, and kind of get into a discussion about When you're a serverless provider, the options you have to reduce prices, and these might be things you might want to talk to other cloud providers and say, why don't you do this because it's cheaper for us? That'll come at the end. Right now, how our platform works is we have latency-based DNS routing to a data center that's to a mini data center that's the closest to your end users. And when your end users get to this close by mini data center, we have a serverless stack that calls into a local document database. So the idea is, if we're here, we're going to call into a data center that's probably about 100 miles away. It'll take 15 milliseconds, and we will do our processing, a serverless function that calls into a database. It reads and writes data all at that data center and responds immediately. It's quick, it's efficient, and then there's a lot of magic that syncs this data that's generated all over the world and deals with all the conflicts. So when you're new, you try to be as API compatible as possible. So we use the serverless framework, which gave us configuration compliance. It makes the same app that you run on all the cloud providers with the serverless framework, you just run on ours. And that implicitly means that the way we define functions is the same as everybody else. And then we put in a lot of effort. So if you have an application running on DynamoDB, we have a data layer that's very similar, and we have some shims that basically have the same data APIs, which is the demo will be the exact same code running on AWS and running on Cohero. So if I get into the code, and this is really, really boring and too small, right? Anyways, this is like the simplest thing. It looks exactly like every other serverless code snippet. You go in, and this one just gets a piece of data with that data get call, and then it returns a HTML response object, and that's how you get a piece of data and respond with it. This is just the simplest code possible, just kind of a code snippet, and it's meant to be boring, as this one is. When you update one, there's one line in there that says increment the value by 1, and that's how you do an update. So these are basically just to show you how boring and non-innovative our data API is, or code API, and that's done on purpose. Okay, so I'm talking about all this stuff. You're taking a centralized app and you're making it decentralized. And people kind of don't know what we're talking about when we say that. So we chose an e-commerce site that has a fair amount of functionality. There are users, you can look at products, you can look at brands, you can add stuff to carts, you can buy stuff, you can comment, you can rate, it's a very simple, straightforward application. But it does have enough functionality that it addresses certain actions that are difficult to decentralize. So there are some tricks when you take an application and spread it all over the world that have to be dealt with. And the goal of this demo is actually just to get into those use cases and kind of show everybody what happens if you want to go multi-region or multi-data center, or what we do, which is multi-CDN pops everywhere. So the demo code is real simple. It's just a bunch of web requests. Basically, every little part of the web page is a separate request. 34 functions. There are some that are interesting. So the second line, it says there are 2 that modify group data. There are certain data modifications like ratings or comments that a lot of people can be modifying at the same time on a lot of different data centers, and those you have to model specifically to be group data. And then there's this thing we call spot, which means single point of truth. There are some things that cannot be decentralized, so we have APIs for that. So the demo is, it's on GitHub. It runs the exact same code, same data API, runs on Cohero and AWS. And then I got lazy, and I just videotaped this last night, figuring that I wouldn't have to talk to it, and that I could summarize the page speeds afterwards. Anyways, this is basically the web application. This is the e-commerce demo right here. At the top, you have your top brands, you have your top deals. This is a guy who's already signed in. He has his recommended products, he has the stuff he's recently viewed, he has a cart, he has favorites. At the top, where the mouse is right here, it's the duration to load the page. So this is now Cohero, and I'm just going to kind of surf this demo e-commerce site, and it's going to be very evident that the user experience and the page loads are significantly faster than AWS. And then we'll also kind of get into which one of these pages don't really centralize or decentralize that easy. So when we start out, it's a 1/10 of a second, or sorry, 2/10 of a second. We click on all categories. It's pretty quick. It's a nice feel. We go to specific men's hoodies. We go to all the brands. We go to specific brand of Fila. Okay, what has the guy purchased? We go to purchases. And then we go to specific product detail. And the reason I didn't want to talk and do this at the same time, because who cares? It's just an e-commerce demo. This is not really what I'm here for. I just wanted you guys to see the application and then get a feel for when we switch this by clicking on that little EC2 thing, the difference in user experience and feel. So this is now slow and jerky and things are kind of coming in. And it's about 13 times slower on average. So stuff comes in slowly, and it's not the best architected web application, because it makes all these separate requests, but it really is easy to do in a serverless fashion. And also a lot of web pages that you go to are not built that well. They have an average of 100 objects. So the same thing on EC2 is a lot slower. And that's essentially what we sell, is user experience and low latency and robustness. So here's a summary of the page speeds. When you look through all of them, in the end, Cohero was about 13 times quicker, and it's pretty easy to tell that the user experience was a lot better. Let me go to full screen. So now I'm going to get into some of the topics that when you guys decide to go multi-region, or if you use Cohero and just spread your stuff out to the edge, some of the challenges that come up, some of the difficult things that happen. And the first one is what we call single point of truth. And this is in every application you have this. You have, say you're trying to get unique usernames, right? You can't distribute that. You can't have 10 people at the same time trying to all get the username Joe, because 10 of them will get it. Same thing happens with inventory. You don't want the last vacuum cleaner being sold to 10 people at the same time. So when you distribute an application like this, you have to have hooks that actually centralize certain parts of it, because there are some things that just fundamentally do not distribute. So we have hooks that you basically say, boom, the register function or the purchase function is a single point of truth, and it's all sent to a single data center, which is by definition centralized. Okay, and now we get into one of the more, it's a very important data guarantee that happens, that becomes more important when you spread an application. So you guys probably all know ACID guarantees. You can also run ACID through Google Spanner. It's just slower than what we do. There's another guarantee called Causality. And when you decentralize an application, if you do not have a strong data guarantee like Causality, you get all these race conditions that eventually corrupt your data in very hard to reason about ways. So one of these ways is there's client causality. Your client will do certain things, like say add an item to your cart and then purchase the cart. And if those requests go to different data centers, or since we send all of our purchase requests to a single data center, because it's a single point of truth, you get these race conditions. They look like this. You add to the cart. After you're done adding to the cart, the replication goes to the other data center, and you get a response. The trick we do is we put some information in the cookie that we pass to the next request. When the buy cart comes, there's a race condition. Who's going to come first? Is it going to be the add to cart, or is it going to be the buy the cart? If the buy the cart wins, then you've essentially corrupted your business logic. You would have nothing to buy. You'd probably get an error, and then later when the add cart item came, you'd add something to it breaks your business logic, and this is a simple example. When you get into complex applications, the race conditions get a lot worse, and if you don't have a strong data guarantee, you will continually corrupt your data in odd ways. So what we do is we add causality that basically says, this buy cart will wait on the add to cart if it hasn't arrived at that data center yet. It's harder to do than you'd imagine. It requires a bunch of vector clocks and a bunch of other stuff, but we have a good solution. The same thing happens in the data layer itself. So if you, say you have somebody comment at this data center on a product, That gets replicated, it goes over to this right one where this guy does a reply to it, and the replication of those two both have a race condition. And if, in this case, the reply comes before the comment, you would again corrupt your data. So you need something, you need a strong data guarantee to ensure that that doesn't happen. And I don't know of any other products that actually do this, right? Everyone else that does, except Spanner, which is a different trade-off that I'll get into in a second, but everyone else that does multi-data center replication just ignores this, and you get, you essentially corrupt the intent of your business logic. And it's hard to understand because I'm doing these weird pictures, but it's the best way I can explain it. I figure it makes sense, right? The race conditions. Maybe it doesn't. Okay, another feature of our platform is we have all of these little mini data centers, and they are caches. So another thing you want to think about is if you're replicating your data to tens or hundreds of places, or even really 5 places, do you really want to replicate your full data set? It takes a lot of storage, and it takes network, which is even more expensive. So we have a cache model, which means, you know, the West Coast is going to be heavily cached on the West Coast mini data centers, and the East Coast and Europe, and you know, it naturally caches just due to it being hot data. The gotcha there is if you try to scan a cache, full table scan on the cache, or you try to query a cache, there's a lot of misses, so you get strange results. So we're thinking of putting in optional global tables, but this is just how our platform works right now, and it's a lot cheaper to do it this way. Honestly, when you replicate your data to many data centers all the time, it's expensive, you know, in 2 dimensions. So one more thing I want to talk about, group data. When you have product ratings, or you do comments, or you like something, or you do a chat, that's a lot of people that are basically editing the same data at the same time, and it's a synchronization challenge or nightmare, however you want to put it. We have CRDTs, which are conflict-free replicated data types, and they're naturally built to have a lot of people modifying data at the same time. If you use something that uses last writer wins, and I know you guys aren't all expert in this, and I'm talking about last writer wins, you might not know what I mean. It's Cassandra or Dynamo global tables or some other NoSQL things. You get odd data corruption, so I want to tell people about that. And what this gets to is, you know, there's a comparison of what databases you can use when you geographically spread your application out. And the first 2 options are pretty good options. There's Cohero and Google Spanner. The last one, I really want to tell people they need to be very careful that they understand the pitfalls, the race conditions, the data corruption that can happen when you do last writer wins. So the first 2 are good options. The third one I don't recommend doing. The differences between Google Spanner and Cohero are Spanner has ACID, which is like an awesome guarantee. It does have the drawback that when you spread out an ACID database to, say, the East and West Coast, you have to do a 2-phase commit every time you write data, and you start to get down into the single digits transactions per second. So you get dog slow. Cohero doesn't do that. It doesn't give you ACID, but it gives you low latency. You can do thousands, millions of transactions per second. Everything syncs up asynchronously after the fact. Now I want to talk to you guys about when you're a cloud provider, some of the options you have, and just kind of put some ideas out into the community about how to reduce costs for serverless providers, which means it costs less for everybody else. So there are some options that we have. Some of them you guys probably know, and some of them you don't. I'll just go through them individually. So the first one is per millisecond billing. Has anyone wanted this as a wish list item? It is for edge requests, which are always very short. It's a huge saving. All the other providers, they do 100 millisecond interval billing, and a lot of functions run a lot quicker than that. So that's one thing that we do that at the edge it makes a lot of sense, because at the edge you're never doing like a 5-minute function call. You're doing very short, low latency requests. Another thing we do is we offer really low RAM options because we're doing short requests. And this allows us to basically pack more containers. So I don't know if you guys know this, but a cloud provider, it takes a single function, and if you call it once, it has a container. If you call that same function 5 times in a row, or 5 times concurrently, it will spin up 5 containers. So basically the more RAM you have, the more resources it will take. And also, we have something to address this, which is customers can elect to put a bunch of functions into a shared container. A lot of functions are happy to coexist in the same container. And again, this comes down to resources. We can save a lot of money by not spinning up new containers for every time a new function is called. And also, if a container is not busy, we send it a request, which is not something that other providers do. The reason being that there's a very strange guarantee that serverless has given to everybody, that function as a service has given everybody, that you have your own dedicated container for every function call, which is really weird, because if anyone's run their own web application, you don't have that at all. You have tons of concurrent requests going on at the same time, and a lot of the time, that's fine, right? And it's orders of magnitude cheaper to provide. Your average container doing a request is actually taking a request, doing I/O, waiting 6 lifetimes, and then doing a little bit more compute. So it's a terribly inefficient way to architect on the provider side. And then finally, and this is kind of out there, but Cloudflare workers did it, you don't even need containers when you do serverless. A good example is browsers, right? Browsers have, you have all these tabs open from different companies. They're all running JavaScript at the same time. They're all sandboxed. You can do the exact same thing as a serverless provider. And when you can do that, you don't need containers. You don't need to start them up. You need to shut them down. They don't take any RAM at all. The big difference there is that a lot of people do serverless now. They call a function, and they take a whole bunch of stuff from S3, and they build this container, and that's their function. This doesn't allow you that opportunity at all. So this is a kind of a pure function as a service without any operating system. So these are just thoughts that we had, things that we examined. We do not do this one because it's a radical departure from what everyone's used to. And then finally, and this is just something I wanted to ask people, at the edge, at the CDN edge, I wonder if JavaScript is enough. We only have one language in our browsers, right? Nobody here is using Flash or VB script, I'm imagining. So my question is, at the CDN edge, do we need Python, C#? And the reason I say this is, it's kind of selfish, but when you're at the edge, you have these mini data centers. They're called points of presence, right? And they're not like a cloud region. They're not hundreds of thousands of machines. They're like hundreds or thousands of machines. You have constrained resources, and those have to serve thousands of customers. And for that reason, you really need to optimize what you're doing. And a single runtime can be optimized for that. So that was just something I wanted to kind of put out there. May or may not happen, and there are people that would probably be like, I will never program JavaScript at the edge. But I would like it, because I think it's the best way to handle the resource constraint problem that happens at the edge. All right, so that was it. If you guys have any questions, and I realize that this is not like a simple serverless concept that I'm explaining here. It's pretty advanced, and a lot of you guys are first time with serverless, so you're probably like, what is he talking about? And others of you are just a single data center, you're cool with that, but eventually there are huge benefits from decentralizing your application. Like probably all of you use CDNs right now for the exact same advantages. You offload it, it's close to your users, it's very robust, and in the end, it becomes cheaper. So, questions? So the single point of truth gets directed to a single data center. And then within that data center, we're just using basically our data layer. So it's not because we're actually proxying requests. When we say single point of truth, it means a request comes to this data center, comes to this one, and they all go to one spot. So it actually becomes a centralized one. So it's kind of not a consensus algorithm, but rather we're just sending everything to a centralized spot, and every mini data center that we have is a cluster of, first you have load balancers that are like API gateways, and then you have serverless servers, and then you have cluster data layer. So every mini data center has multiple clusters. But there's no consensus. It's just basically like a document store. Like they don't use consensus, they use, what's the word? Synchronous replication between two machines for backup. The client can directly query that single point of truth. So all you have to do is set the function that is querying that data to be single point of truth, and everyone gets directed to this centralized object. Everyone goes to the same data center. If they're looking for key A, it's always going to be on the same machine, key B, unless there's failovers at the time. So that part's simple, if that makes sense. It's just a huge data layer. So it's like a Dynamo or a Cassandra, or just a distributed database. And everyone goes to the same data center in this single point of truth. So we say we're half the cost, and we compare it to using API Gateway with Lambda and DynamoDB. And then we have two different pricing models. But one is we have like if you have a very short request that only does a couple DBIOs, we just give you a set cost for the request with the DBIO, and it's cheap. If you go and do more complicated stuff, our pricing model is, it turns out to be about half of what you would get if you ran it on AWS, so 50%. And most of it is because of those tricks I was talking about. We use less resources. We're just economical because the reality, what his question was, we only do short requests, so we optimize to it. Yeah, we can, we will, but you have to be a lot bigger to be free tier. We're not, that's the get them hooked and then get them in, and we're not there yet, but we aspire to it. Basically, when a customer signs up, we give them a subdomain of Cohero. Like if you're like, your company's name Hula Hoop, you'll get hulahoop.cohero.com. And then we have a wildcard that goes to our servers, so that part's actually pretty easy. Does that make sense? Right now, it's just you upload your functions that call into our data layer. That's essentially what we're offering. So there's not much security there. If you want to add in your own keys, you can add them in as data right now. Yeah, so that's the really hard part, and I spent a long time myself actually building a data layer that is based on some new academic work. It's called conflict-free replicated data types, and what it does is and I did a blog for serverless.com. It's on their blog. You can check it out because it's a difficult concept to wrap your mind around. But essentially, what it does is it frames any modification you do to data as a commutative operation, and commutative operation is like if we're throwing money on a table, we can all throw money in any order, and it always adds up to be like $100. So it doesn't matter what order all the money comes in. That's what commutative means. So you can take that mathematical property, and it's very easy to do things like counters that increment and decrement, or you can do arrays or trees or linked lists that build using certain properties. And you can basically offer a data layer that offers anything JSON does. And that's the way that you can have these different independent actors writing their data locally and then syncing asynchronously afterwards, and everyone not only syncs up, but the manner in which the conflicts are resolved between differing people is very intuitive and logical. So I'm happy to tell you more about that. It's a very interesting new advance in database academia. Like, it's not like all database papers are like 30, 40 years old, and these are like 6 years old. So they're brand new. But that's our data layer. And I have a blog where I went through all these silly examples and tried to really spell out what I'm doing. The general answer is anything that's latency based. There are IoT applications. There are actually people send out devices all over the world, and they want them to call into a close by cloud presence. There are gaming use cases where people have, you want your game to run first person shooter, MMO, stuff like that. There are ad tech use cases where you don't want to wait on your ads, stuff like that. But the key, uniting factor between them is low latency, and it's user experience, really. It's people that want, like these days, if I wait on anything I do on my mobile phone, I get frustrated. And I personally I know exactly how to eradicate that. Like, I know I have a platform that solves that problem for every one of your end users. So I think the future of it is going to be anyone that cares about latency, which is going to be everybody. But in the beginning, it's mainly the latency junkies. IoT, gaming, ad tech.
Cool. All right. Thank you very much, Russell.
Cheers. Thanks.